All right, so where is the marker? There it is. So what we're talking about right now is implicit differentiation. So what happens is that we're given explicitly y equals f of x as of now. But what happens if the expression is given implicitly? So if we have like x squared plus y squared equals 1, or if we have something ugly like 2xy plus 3x squared y squared equals e to the x, or if we have ln of xy plus 2y squared equals sine y, right? What happens then? How do we differentiate these ones? Well, so this introduces, I was just reading something in the notes there, but this introduces the topic of implicit differentiation. And what that is the fact that y is a function of x, essentially. So wherever we see an expression involving y, we differentiate it using the same rules as before, but we also write y prime. We write y prime or dy dx with it as we're following the chain rules. So if I had x squared plus y squared equals 1, man, sorry. If I differentiate that, I get 2x plus 2y dy dx equals 0. So what I would do is solve for, because it's the chain rule, right? So the derivative of y is this dy dx. So what happens is I can factor out 2 from x plus y dx. Okay. And then what I could do, get rid of the 2. So then dy dx ends up being minus x over y. So that's the expression implicitly to find the derivative of x squared plus y squared equals 1. So let's look at 2. Let's look at 2 for this implicit differentiation. It's a fun day to do some implicit differentiation. So we have 2xy plus 3x squared y squared equals e to the x. Then we just differentiate everything on both sides. So this is a product rule, and this is a product rule, and this is just by itself. So I go 2x dy dx, because the derivative of y itself would be 1, but then you do the chain rule, so dy dx plus, it's a product rule, so 2 up there. And then you would also just do y plus 3, 2x y squared plus x squared 2y dy dx equals e to the x. So I just want to make sure that I don't severely So then obviously you would go ahead, I'd FOIL this back in, so I'd get 2x dy dx plus 2y plus 6xy squared plus 6x squared y dy dx equals e to the x, essentially. So what happens now is that I can rearrange this in some way. Like, these are two terms that have dy dx in them. And I want to group those together because I want to essentially factor out dy dx. So what I would do is I'd have 2x dy dx plus 6. Okay, I have all that. And then I have dy dx and then so dy dx equals e to the x minus 2y minus 6xy squared all over 2x plus 6x squared y. So that would be, that d's down there would be the derivative implicitly when you solve for it. How many more examples we got here? There's one more, and then we're going to do applications of derivatives. How do we use them in word problems? How do we apply to real life? So, if we have ln xy plus 2y squared equals sine y. If I differentiate this, 1 over xy times y plus xy prime plus 4 y prime equals sine cosine y prime. That looks pretty good to me because there is a y that I have to do a chain rule, and I get all the y primes by themselves, so that's secretly, these y's cancel, so 1 over x plus xy prime plus 4 y prime equals cos y prime. So I have more terms that have y prime than not. I have 3 terms that have y prime in them, essentially. So I'll put those all on one side. I'll leave the 1 over x over here. So if I were to rewrite this, I have cos y prime minus xy prime minus 4y prime equals 1 over x. So y prime equals cos of y minus x minus 4y 1 over x. So y prime equals 1 over x cos y minus x minus 4y. Okay, so that would be the answer for that implicit. We're going to start a new video for applications.